All right. Welcome, everybody. I'm Marcos Guimarães, and we are here at the Lawrence Center in a workshop of quantum magnetic materials with Joaquín Fernández Rossier and Rembert Duine and Zeila Zanolli to discuss about especially the fundamentals of two-dimensional magnetic materials. Maybe I'll start with our co-organizer, Zeila. What is special about two-dimensional materials, and what brought you to this field?
First of all, is the change in dimensionality, going from 3D materials like bulk, like common materials, to 2D materials really open a set of possibilities which are not possible in 3D. So they are more sensitive to any perturbation from the external world, just because they are all surface. And this, on one hand, makes them very difficult to treat, both experimentally and theoretically. But on the other hand, it opens the door to many possible applications. They're very versatile. And there is a lot of very interesting fundamental physics hidden there. So I think they are challenging, and that's why they are interesting. And we see that you can think of any possible interaction also with other degrees of freedom, interaction between magnetism and charge, or with light, and so possibilities to control, not just having this very nice quantum phenomena, but also control them. So that's the interesting bit for me.
No, Joaquin, do you agree? Do you have something else to add?
Yeah, no, I agree with that. I mean, the way I think about it is like this. In your question, you had two questions, right? One is why we got into this and why these materials are special. So let me begin with the first question. So all my life I have worked on spin systems, okay, on spin physics in different systems, like quantum wells and very early on, and then magnetic semiconductors. And then when graphene was discovered in 2004, I also started working on two-dimensional materials like graphene. So for me, it was totally natural to think about the possibility of having magnetic 2D materials. So when they were reported, the discovery was reported in 2017, we were ready and we jumped into that. And now, as of why they are very special, well, if you think that magnetism and spin physics is very interesting and very special, and 2D crystals are also very special, these two things together make the materials special square. Okay, so yeah.
And Rembert, then what brought you to the field?
So my interest over the last few years has been mostly magnon transport, and I think there are some very interesting promises of 2D materials for magnon transport, in particular topological magnon transport. So let's say 2 dimensions is very prone to topological states of matter. And so you could imagine exotic lattices where you have topologically protected magnetic edge states, for example, that can be used in even in applications. There could be two-dimensional spin superconductors. So these kind of exotic. So I think it's really going to 2D magnetic materials really kind of brings exotic magnetic physics into possible applications for spin transport. So that's kind of what I'm really interested in, to go in that direction.
And do you see any, you said, well, it's very, all these very interesting properties, right? But do you see any, anything, what are the most interesting things for you? Do you really think that the topologically protected magnon states, is that the
So that's definitely one of the kind of the big things, if you can actually demonstrate the existence of those states, which is not so easy because they are, contrary to electronic edge states, they are actually at high energy, so you have to think about how to bring them down. But if you can prove that they exist, if you can use them to transport spin from, let's say, from A to B, that would be one of the most promising things.
And is that the correct material or material system to probe that? I mean, what is special about these 2D magnets?
Right, so at least there are some candidate materials where that basically host what people believe will be the Haldane model for magnons. So these are hexagonal crystals with some magnetic interactions, exchange, Leszczynski-Maria. that can typically host topological edge states. So they are very basic models or very basic materials that already host these topological edge states. So I think in that sense it's very promising that one of the two-dimensional magnets will actually have those topologically protected magnetic edge states.
I see Joaquin nodding, so you clearly agree. But for you, I mean, you come from a different perspective, right? Rembert is going more towards the magnonics. You're more into the spin systems. And do you see any unique property of 2D?
Well, first of all, I really like magnons too, topological magnons in chromium iodine, okay, for instance. But another thing that is really potentially unique of magnetic 2D materials is you could have a chain insulator, a quantized anomalous Hall insulator. So that would have the same properties that a quantum Hall bar, but at zero magnetic field, okay? So there, instead of having topologically protected magnons on the edges, you would have electrons going only one way, okay, with quantized conductance, okay? That would be really cool. And there are some materials that are close to doing that. And I think this is a very interesting line of research.
Yep. And for you, Zeila?
Yes. So one of the very interesting things that you can do with the 2D magnetic material is to play with proximity effect. So if you put two material in contact, so across their this interface that you create, you can induce magnetism from a magnetic material into a material which is not magnetic, or you can change in very fundamental properties like spin orbit coupling of the complex material. And what I really like is that you make new properties emerge at the interface. So what happened there at the interface is not just the sum of the properties of material A and material B, but is something new, which you cannot achieve if you take them individually in a separate way. So you can enhance property, you can suppress also some properties. So it's very rich playground for physics and technological application. So it really opened the gateway towards quantum material for technological applications.
Yeah, I think related to that, I think one of the interesting things of 2D materials, something that we mentioned in the beginning, I think was this coupling, this strong coupling with the external world, right? Could be light, could be strain, could be gating. And I think that's something that is quite special in the materials in some way, right? I mean, I work a lot with the light matter interaction, and I think 2D materials have a very strong magneto-optical signals, and they're that you cannot get in a regular 3D system. But then there's always a question, right? If you're doing 2D magnets, and you get questions from the referees saying, okay, we can also do that with a thin YIG. Is there something that would be that cannot be done with thin YIG, right? It would be in principle a 2D system if it's thin enough.
So I think, for example, the topology that we just mentioned, that's not something that you would have in YIG naturally. Of course, you could try to engineer it, but somehow, that would be a bit at larger length scales rather than at the atomic length scale at which you would want it. Second, I think YIG, it has such a large unit cell that even thin YIG is still very thick to compared to the 2D magnets that we would have in mind ultimately. So that's also a drawback, I think.
Yes, connected to this, I would like to add one of the open research questions of the moment is where is the thin film limit? So where is the limit between 3D, 2D and quasi 2D? What happened on the properties when you play with the dimension? Where is the threshold of the change? So for instance, you can have a material which is topologically in 3D and you go down and you thin it and then it's still topological, but then how thin it should still be and preserve these properties. Also for ferroelectric materials, there is a similar problem. So here we are really playing with something which has an atomistic dimension, And so this is not obvious, not a trivial question to see where is the limit.
I always said, maybe you can clarify something for me, because I always thought, okay, how thin is thin, right? And this would depend on the out-of-plane exchange, interlayer exchange constant. Isn't that a simple...
It depends if you have materials. It depends on the material. It depends on the chemical bonding. So on the intrinsic nature of the material. If you have a van der Waals material, then probably as the let's say the strength that the bonding between the layers is quite weak with respect to covalent or other material, then you can say, okay, there is a chance that these properties are preserved even if you go at a very thin limit or 1 or 2 monolayer. But this is not always the case, because you still have some interaction between, let's say, the external surfaces of this few layer material, and this plays a role, and you can change. There is an hybridization of states. Also depends if you have excitons, what is the range of how extended they are. So there are. This is very much material dependent, and that's why, like in my research, I do simulation of materials from first principle. So it's not a one-size-fits-all model, but I study case by case. So it's very material dependent.
Joaquín?
Yeah, sorry. Following up on this, I think it depends on the properties, right? For instance, take the case of molybdenum sulfide in bulk. It's an indirect semiconductor, so it's bad for optics, as you know, right? And now you need to go to the monolayer, if I remember well. Already the bilayer is indirect bandgap, and the monolayer only is direct bandgap, okay? So for that particular property, that's the answer, okay? Now, for other, for instance, in quantum confinement, if for using enough to have quantized levels in the off-plane direction, then what matters is whether the splitting of the difference of bands is larger than temperature, okay? So for magnetism, I think it's the same. It depends on the property. The thickness that gives you truly different behavior will be different, okay?
And in this, since we like magnons, right? I think I also know that the magno-magno interaction for low-dimensional systems should also be enhanced, right? Is there something that we can? Is there a smoking gun experiment or a pattern that we would see to prove, maybe using that correlation to say, okay, this is when we have this threshold interaction, then it starts to become 2D.
Well, that's a difficult question, I think. For example, this question is not understood in ongoing experiments that were done recently in the context of thin YIG, right? As you know, probably very well. So I don't think it's an easy question to answer right away, and it will probably depend also on a lot of material details. I think. So I think basically not only magnon transport, but I think more general magnetic interactions will be very important and can lead to all different kinds of ground states in 2D. That I think those are more likely the unique aspects of 2D for the magnetic properties, at least, and interactions. But I think Joaquín would like to add something here. So.
Yeah, thanks. About how you could tell that you have magnon-magnon interaction, this actually has been already seen experimentally in tunneling experiments, and the smoking gun is the fact that the energy of the magnons depends non-linearly on the magnetic field, and this is an effect that arises from an interaction between magnons. Basically, the effective field felt by the magnons depends on the magnon density. Okay, and that changes with the magnetic field.
And is this a 2D thing per se, or?
I think the magnons are. It could happen also in 3D.
Right.
Okay. I'm not totally sure the effect will be stronger in 2D. Mm-hmm. That's a good point. I don't know.
Yeah, I think in 2D there are, going back to magnon interactions, there are also some experiments and proposals for looking at, let's say, 2 coupled layers, and then you can also play a bit with the interaction between layers, between magnons in one layer and the other. So that would also give you a nice degree of freedom to do something with the interactions.
Yeah. And I think related to that, I mean, we're moving on to types of unique opportunities that 2D magnets give us. And Zeila mentioned also the heterostructures, right?
Yes, that is one thing. You can play with different stacking or with this twisting, a different alignment. And another possibility that I see is in defects, as you can have magnetic defects. And you can think of using this for quantum bits or any quantum technology. So here there is an interplay between, for instance, the light that excites a sample, your magnetic level in the sample, excitons. So it's a very rich physics. And this, there are some experiments and a bit of theory as well, but is still largely unexplored from the technological point of view. And so I think here is really where we need to educate the workforce of the future, because this is going to create a lot of work for the next generation.
Yeah, and I think here, before moving on, I think commenting on the heterostructures, I think it is also very difficult to get a correspondence between what we do in the lab and what the theorists are doing, just because the supercell is so large, right? So I think one of the challenges there would be to have a way to explore this twist angle space, both in theory and experiments.
Yes, also one of the big challenges is to make a correspondence between theory and experiment. Because in experiment, which is like real life, there are a lot of effects that occur at the same time. And when you do a model or you do a first principle simulation, you have less degrees of freedom. So you can really control what you have in your theoretical experiment. And then it's a very different situation. Also, there are constraints of what you can model, what you cannot model. And there are the limit and the complexity, and why this is still very challenging.
And I think you mentioned there that there will be a challenge for the next generation, right? And since we're talking about that, and if we have to convince a master student to pursue their career, their PhD in 2D magnetic materials, what would you use to convince them?
Yes, I would say of course, that this could be the door of the new set of technologies. And then this person will have the opportunity to join as an active participant the change in, it will be really a change in paradigm on how we do it. Then there will be a lot of other skills that the person will acquire, either at the level of technical, computational, or programming or experimental, that can be used in any other fields. And then last, maybe I would like to transfer the passion, the enthusiasm, and the curiosity for this emergent physics that opens here in the 2D magnetic materials.
I saw Rembert.
Yeah, I just wanted to add, so I completely agree with what Zeila just said. I just wanted to add a perspective from somebody who works in a theoretical physics institute and has to compete with PhD students wanting to do quantum gravity and whatnot. So I would say that if you take a very generic point of view, like 3D is kind of boring in the sense that it's mean field. I don't think it's really boring, but that's 1D you can solve exactly. So 2D is right in between and is very hard. So that's so it's kind of, and it's a special dimension for everything. So you have topology, geometry, and even quantum gravity is kind of unique in 2 dimensions. Mm-hmm. So I think especially for theorists, it's kind of like the coolest dimension to live in. And there is a perspective for applications and so on. So I think it's that together would really...
I think being able to use your theory and then have someone test it in the lab in the next month is
to go from
quite...
exotic physics, like super exotic physics, to experiments and potentially applications. I think that's
which is something that you can't do in quantum gravity, right?
Right. Yeah.
Joaquin, what would you say to a master student?
Well, I would add to what they say. Okay, well, the checklist is first I'm gonna learn things that will be useful anyway once the field is fading away. and this is clearly the case.
Hopefully in several years from now.
Yeah, no. Clearly the case that you will learn things useful in a broader context, okay? And then the second is whether there's a community that cares, okay? Because you can be doing research that nobody cares about, okay? If you do some fancy problem on quantum gravity that the community is only 9 persons, then you are really limiting your impact, okay? And then the other one is whether there are questions that can be solved in a reasonable time, okay? And I think again this field of research is clearly there, okay? We are asking questions that matter and are exciting and can be solved soon. So that would be that.
Yeah, and I think also the fact that the field is there and then we can apply it, right? I mean, it's we apply it to electronics and semiconductors, and that is an industry, a very big industry, and especially here in Europe, we are trying to have more and more people working in this field, and I think that's quite important. So this means that they will have a job guaranteed after they finish their PhD, and I think that's also kind of maybe more pragmatic, but also important, right?
Indeed.
Yeah.
All right, and we reached the end of this episode, a special episode from the Quantum Magnetic Materials at the Lawrence Center. So would like to thank you, Joaquín, Rembert, and Zeila for joining us today.
Thank you, Marcos.
And see you next time.
Okay, thank you. Bye.